A tenth of a second once
Oh,
cost Amazon billions of dollars. Every 100 milliseconds, a page got slower. They lost 1% of sales. So the biggest companies on earth went to war over speed. Google, Netflix, Amazon. Almost all of them won with the exact same trick. Not a faster server, not a bigger database. A trick so simple, once you see it, you'll wonder why every computer doesn't work this way. It's just remembering what you've already looked up. That's caching. But to really feel why this matters, let's step inside a library. So let's imagine something a little different. Picture walking into one of the biggest libraries in the world. Thousands of shelves, millions of books. You walk up to the librarian and ask, "Who invented Java?" She smiles, walks down into a massive archive, searches through hundreds of books, finds the answer. Walks all the way back and finally tells you, "James Gosling." It takes a while, but you get the correct answer. Now here's where it gets interesting. A minute later, another person walks in and asks the exact same question. "Who invented Java?" What do you think the librarian does? She walks all the way back down to the basement, searches the same shelves, finds the same book, walks all the way back and gives exactly the same answer. Then another visitor arrives. Same question, same trip. Another visitor, same question, same trip. Again and again and again. Now let me ask you something. Does that feel efficient? Of course not. The answer hasn't changed. Yet the librarian is repeating the exact same work every single time. At this point, you'd probably stop her and say, "Why don't you just keep that book on your desk?" Exactly. That's the idea. She walks down once, brings the book back, and keeps a copy right on her desk. Now the next visitor asks, "Who invented Java?" Does she walk downstairs? No. She just opens the book already on her desk and answers immediately. Same answer, much less work. That, right there, is the entire idea behind caching. In software, we call that desk a cache. So let's map this story to a real application. The basement represents your database, where all your original data lives. The librarian represents your application server. And the desk? That's your cache. A much smaller, much faster place that keeps frequently used data close by. Now notice something important. The cache doesn't replace the database. The database is still the source of truth. The cache is simply a shortcut. Instead of making the same trip over and over, the application first checks whether it already has a copy nearby. If it does, it saves time. If it doesn't, it goes to the database. That one simple idea changes everything. Now let's leave the library for a moment and watch what actually happens inside a real application. A user opens a product page. The request reaches your backend. Before your application even thinks about querying the database, it asks one simple question. Do I already have this in my cache? This time, there's nothing there. The cache is empty. So the application has no choice. It sends a query to the database. The database searches, finds the product, and returns the data. The application sends the response back to the user. But before the request is complete, it does one more important thing. It stores a copy of that product in the cache. This entire situation is called a cache miss. Now watch what happens a few seconds later. Another customer opens that exact same product page. The request reaches the application, and again it asks, "Do I already have this data?" This time, the answer is yes. The product is already sitting in the cache. No database query, no expensive lookup. The application just reads the cached copy and returns it instantly. This is called a cache hit. Let's compare the two side by side. During a cache miss, the request travels all the way to the database. The query runs, The result comes back, a copy is stored in the cache, and only then is the response returned. During a cache hit, the journey is much shorter. The request reaches the application, it checks the cache, the data is already there, response sent, done. That's why cache hits are so valuable. Every cache hit is one less database query. One faster response for your users. Now here's an interesting question. Imagine your application gets 100 requests. How do you know if your cache is actually helping? Say 95 of them are served straight from the cache. Only 5 have to visit the database. That's fantastic. This is why engineers care about the cache hit rate. It's the percentage of requests served directly from the cache. 95 hits out of 100 is a 95% hit rate. And as your app grows from one user to millions, a good cache means most requests never touch the database at all. Instead of 1,000,000 queries, the database might handle only 50,000. Now you might be thinking, if caching is this useful, why don't we just store everything? It's a good question, but the cache has one big limitation. Memory is expensive. A database might store terabytes. Keeping all of that in memory just isn't practical. A cache is meant to be small, fast, and selective. Let's go back to our librarian. Her desk isn't as big as the basement. She can only keep a handful of books nearby. Eventually, another visitor asks a completely different question. She finds another book, returns to the desk, and realizes there's no room left. Now she has a brand new problem. Not, where do I find the answer, but which book do I throw away? This process is called cache eviction. Whenever the cache is full, it has to remove something before storing new data. But how does it decide? Imagine the books on the desk. One's been used 5 times in the last minute. Another hasn't been touched in 2 hours. Which would you remove? Most of us would drop the one nobody's used recently. That's exactly how least recently used, or LRU, works. When the cache runs out of space, it removes the item that hasn't been accessed for the longest time. LRU isn't the only strategy. Some systems use LFU, least frequently used, which drops the item accessed the fewest times. Others use FIFO, first in first out, which simply removes the oldest. There's no universal winner, but they all solve the same problem. A cache is small, so eventually something has to go. So far, our cache seems almost perfect. Faster requests, less database load, and it's smart about what it keeps. But there's one problem we haven't talked about, and it's the reason caching is much harder than it first appears. What happens when the data changes? Let's go back to our product page. A customer opens it, the cache has it, cache hit, instant response. Everything's perfect. Now, a few seconds later, an admin updates the price from $50 to $40. The database is now correct. But the cache still has the old value. Nobody told it the price changed. So the next customer opens the same page, cache hit, instant response. But this time, they see $50 instead of $40. The app is fast, but it's wrong. And that's much worse. Because users can forgive a slow app. They won't forgive incorrect data. This problem is called stale data. So how do we fix it? The simplest solution is surprisingly straightforward. Don't keep cached data forever. Imagine every item in the cache comes with a small timer, say 5 minutes. As soon as it's cached, the countdown begins. 5 minutes later, whether anyone asked for it or not, the cache removes it. This timer is called TTL, time to live. But think a little deeper. Suppose your TTL is 10 minutes and the price changes just 1 minute after it was cached. For the next 9 minutes, every customer still sees the old price. For a news website, maybe that's fine. But for a banking app or a ticket booking site where only one seat is left, 2 people could think they own the same seat. Sometimes, waiting for the timer just isn't an option. This brings us to one of the most important concepts in caching: cache invalidation. Instead of waiting for the timer, the moment the data changes, the application tells the cache directly, "This data has changed. Remove the old copy." Let's see it. An admin updates the price. The application writes the new value into the database. And immediately after, it sends one more instruction to the cache: delete the cached product. The cache removes the old copy instantly. Now the next customer arrives, the cache is empty, a cache miss. So it fetches the fresh $40 price from the database and stores a new copy. Notice something. The cache wasn't updated directly. It was simply cleared, and the next request rebuilt it automatically. This strategy is called cache aside, and it's one of the most common patterns you'll see in real applications. TTL is simpler. Invalidation is more accurate. The right choice depends on how fresh your data needs to be. Now let's zoom out, because real applications don't have just one cache. They have several. Let's follow a single request. You open Amazon's homepage. Where does the request go? The very first cache is sitting on your own computer, your browser. Before making any network request, the browser checks if it already has a valid copy, an image, a logo, a style sheet. If it does, the request ends right there. Nothing even travels across the internet. If not, the request moves to the next layer, the CDN, a content delivery network. Amazon has servers all over the world, so your request goes to the one closest to you. If that nearby server already has a copy, response sent. No need to contact the main application. And if the CDN misses, the request reaches your application. But before touching the database, it checks one more cache. Usually, this is Redis, an in-memory data store built for speed. It keeps data in memory instead of on disk, which makes it incredibly fast. Only if Redis also misses does the application finally query the database. Think about what just happened. The first request traveled all the way to the database, but the second request might stop at Redis. The third might stop at the CDN, and the fourth might never even leave the browser. Every layer moves the data one step closer to the user. And that's exactly what makes apps feel instant, even with millions of users. Now let's put it all together in a real interview. Imagine you're interviewing for a back-end role. The interviewer asks, "A product page is cached in Redis. An admin updates the price, but customers still see the old price for a few seconds. Why is that happening?" Let's think it through. The database was updated, so the database is correct. The problem is that Redis is still holding an old copy, and the app is reading from the cache instead of the database. Now the interviewer asks, "How would you fix it?" There isn't one answer. For a blog or a news site where data rarely changes, a short TTL is completely fine. But for airline tickets, bank balances, livestock prices, or inventory during a flash sale, stale data causes serious problems. There, the app should invalidate the cache the moment the database updates. The important thing isn't memorizing which approach to use. It's understanding the trade-off. TTL is simpler. Invalidation is more accurate. Your job as an engineer is to decide which one fits your system. And that's exactly what interviewers are listening for. Not memorized definitions. The reasoning behind the design. Now remember the question we started with. Why was the first request slow, but the second almost instant? Now you know. The first request had to do all the work. It traveled through every layer until it finally reached the database. And along the way, copies were stored. The browser kept one. The CDN kept one. Redis kept one. So the second request follows a completely different journey. Instead of traveling all the way to the database, it stops at the first place that already has the answer. sometimes the browser, sometimes the CDN, sometimes Redis. And only if every cache misses does the database get involved again. And that's the biggest idea I want you to remember. Caching is not about making computers faster. It's about avoiding unnecessary work. Every request follows the same simple decision. Do I already have the answer? If yes, use it. If no, fetch it. Store a copy and make the next request faster. Everything else you've learned, cache hits, misses, hit rate, LRU, LFU, FIFO, TTL, invalidation, browser cache, CDNs, Redis. They're all just techniques built around that one question. Do we already have the answer? Once you think that way, caching stops feeling like a list of interview terms. It becomes a way of solving performance problems. If this helped it click, hit subscribe. See you in the next one.